Let's talk about carbocations and their stability. So, carbocations are one of the reaction intermediates that are generated during the reaction when a carbon loses a group of atoms or loses a group or a leaving group that leaves with the electrons. That will generate an ion with a positive charge on the carbon. So, the carbon, which normally has bonds, four sigma bonds, will have an sp3 hybridization, while when it loses the group, the leaving group, and becomes a carbocation, then now it will change its hybridization from sp3 into sp2. Now the carbocation, the carbon, will have a vacant p orbital and then gonna have a three sp2 hybridized orbitals that will make the remaining three bonds. The formation of this vacant p orbital is essential for its stability. So before we start talking about the stability of a carbocation, we need to familiarize ourselves with the different types of carbocations. There are three different types of carbocations. The first one is the simple alkyl carbocations, and the second are the allylic type carbocations, and the third one would be carbocations that have other structural features. So let's talk about stability, starting with the simple alkyl carbocation. The simple alkyl carbocations are these carbocations which only have carbons and hydrogens attached, directly attached to the carbon. And we know that there are four different types of carbocation. There are the methyl carbocation, which is the carbon which has three hydrogens attached to it with the positive charge. We have the primary one, which has only one R group, and the secondary, which has two R group, and then the tertiary, which has three R groups attached to it. So the stability will increase from the tertiary to the secondary to primary, and then finally the methyl carbocation, which is completely unstable. So let's explain why this trend, why the tertiary is more stable than the secondary, more stable than the primary, and more stable than the methyl. The first effect, or the first reason, or the first explanation is due to the inductive effect. So the inductive effect is the ability of the group or the tendency of the group to either release the electron density away from it or attract the electron density. When we have the different carbocations, we're going to see that for the tertiary carbocation, there are three carbons attached to the positively charged carbon. Each of these carbons will have a positive inductive effect, which is electron releasing power or electron releasing tendency. So they tend to push the electrons towards the positively charged carbon, and that will increase the stability of the positively charged carbon. And then for the secondary one, we only have two carbons, which will show this positive inductive effect. For the primary one, we only have one carbon. For the methyl, there is no carbons at all. And now we should know or remember that the carbons have much more or better electron releasing effect than the hydrogen. So the effect, the positive inductive effect of the carbon is much greater than the positive inductive effect of the hydrogen. This is why tertiary will be more stable than the secondary, which is more stable than the primary, and the methyl is completely unstable. The second effect that, or the second explanation for that stability is the hyperconjugation. So remember, we talked about how the carbocation will change its hybridization from sp3 to sp2 when it's formed, and it will have a vacant p orbital. This vacant p orbital can actually contribute to the stability of the carbocation through hyperconjugation. Hyperconjugation is the stabilization or the stabilizing interaction that results from the interaction of the electrons in the sigma bond, usually carbon-carbon or carbon-hydrogen with an adjacent empty p orbital. So now when we have our carbocation, we have this methyl group next to the carbocation. The carbon-hydrogen bond here is coplanar. The sigma bond is coplanar with the empty p orbital, and that allows for the interaction between these two orbitals. This interaction will give an extended molecular orbital that will increase the stability of that system. This is called hyperconjugation. But now, why would the tertiary be more stable than the secondary and then more stable than the primary? This How can hyperconjugation explain that? So the carbon-carbon sigma bond, which is the bond between the carbon between the positively charged carbon and the carbon adjacent to it, it's a sigma bond and it's free to rotate. And as it rotates, each of the carbon-hydrogen bond on the carbon adjacent to it will in turn undergo the stabilization effect or the hyperconjugation effect. So if you have a primary carbocation like this one, and then you have this carbon-carbon sigma bond, it's free to rotate. As it rotates, each of the three hydrogen atoms or each of the three carbon hydrogen bonds will become coplanar with the vacant p orbital and will contribute to the hyperconjugation, and that will increase the stability. So if you have a secondary carbocation like this one, now you have six different hydrogens on the 2-methyl group attached to the carbocation or attached to the positively charged carbon. Each of these bonds can freely rotate, and each of the six hydrogen can contribute to the hyperconjugation. If you have a tertiary carbocation, then we're going to have 9 different hydrogens. The increased number of the hydrogen that can contribute to the hyperconjugation, the more stable the carbocation. The second type of carbocation is the allylic type cations. Allylic type cations are these cations when you have a double bond on the carbon adjacent to the positively charged carbon. So if you have a positively charged carbon here and then adjacent to it there is a double bond, this is called the allylic type cation. These allylic and benzylic type cations will be much more stable than the simple alkyl carbocations. The main reason or the explanation for that is because of the resonance stabilization. So as we can see in the resonance stabilization, this is an allylic carbocation. The double bond, here the electrons on the double bond adjacent to the positively charged carbon can move through resonance to give two different resonating structure, and that will lead to the distribution of the positive charge on two different carbons, and that will increase the stability of the carbocation. And even the benzylic one would be much more stable because as we can see from the resonance, there are more than one contributing structure or more than just two resonating structure like the allylic carbocation. So we're going to have the continuous movement of the electron and the distribution of the positive charge as the electrons move on 4 different carbon atoms. So this one will be even more stable than the allylic type cations. And finally, carbocations which have other structure features. So another structure feature that will increase the carbocation stability is the presence of adjacent to the cation center, if there is a heteroatom that has unshared pair of electrons. So, and explanation for that will be also the resonance stabilization. So imagine you have a carbocation like this one, where the adjacent to the carbocation center or the positive center, there is an oxygen with a lone pair of electrons. This lone pair of electrons can contribute to the stability by the resonance effect, and that will mean that actually the positive charge will be distributed between two different atoms, which will increase the stability of the carbocation. And imagine if you even have a structure that has both the allylic one, allylic type, and the heteroatom adjacent. Both of them are adjacent to the carbocation center. Then you're going to have different resonating structure, different contributing structure, where either the double bond, the lone pair of electrons on the oxygen can move to make a double bond, and then will distribute, or the oxygen will have now the positive charge, or even the electrons on the pi bond adjacent to the center of the carbocation can now contribute to the resonance, and that will mean that the positive charge will even be distributed on a different atom. So now you have the positive charge distributed between three different atoms, so this one will be even more stable than the first one.